It's my pleasure to introduce today's speaker, Dr. Petros Stefanou, who is currently a postdoc researcher here at IAG, but has been previously a postdoc at University of Alicante. Here in his PhD in astrophysics from the University of Valencia, and his master's in astrophysics from the National and Capodistrian University of Athens. And today he will be talking about general-relativistic magnetospheres in 3D physics-informed neural networks. So whenever you're ready, Petros.
Thank you very much. Hi everyone, thank you for having me. I am a new postdoc here in IAG, but I will talk to you about the things that I was doing before coming here in Spain. And this is magnetar magnetospheres. Solved using physics-informed neural networks, which is the method that we used over there. So this is a brief overview of the talk. And to start with, I'm going to explain a little bit what are magnetars and why we are interested in them. So magnetars are a class of neutron stars, which have some extreme properties, extreme magnetic fields, the highest encountered in the universe, relatively slow rotation compared to other classes of neutron stars, and very young age due to their very fast magnetic braking. So all these characteristics position magnetars in this pp dot plot, where we usually put all the population of neutron stars. Here in the upper right corner, these red rectangles are the objects that we are interested in. From this type of objects, we usually observe X-ray emission, some pulsed and permanent, persistent, but the most interesting part of the emission is the transient one, which is composed of short duration bursts. So the magnetar is usually quiescent, we don't even observe them, but at some point it emits a short burst in X-rays, followed by some afterglow. Sometimes this activity is longer and lasts for a month or so. Includes many short duration bursts, and in very rare cases we have very energetic, highly energetic flares from them. In X-rays, so energetic that they could overshadow all the rest of X-ray emission from all the other objects in the universe for that short duration. So this type of transient activity is highly believed to be originate from the magnetosphere of the star, which is the region surrounding the magnetar, where we have plasma and charged particles that flow in the magnetic field. Roughly, you can imagine that the magnetic field outside of the star has a dipolar shape, more or less expected. Charged particles move along the field lines, and all this structure co-rotates along with the star, even though for magnetars this is not so important. All the non-thermal emission that we observe from neutron stars in general and magnetars in particular comes from this region, and we will see it comes from parts of the magnetosphere that are not purely potential and dipolar, but they deviate from this picture. So how do we describe the physics of the magnetosphere? In this case, which is usually not what is being done, but in our case we wanted to also include general-relativistic effects because neutron stars are compact objects. So we assume that the spacetime around them is described by the Schwarzschild metric. It's a good approximation in this case. No other contributions are important. The dynamics of the magnetosphere depend only on the magnetic field. All the other forces compared to the very strong magnetic force can be neglected. The gravity of the plasma, the gravity of the star on the plasma, the pressure of the plasma in the magnetosphere, the particle inertia, and all other forces, electric forces, whatever, they are negligible compared to the magnetic force. Also, in the case of magnetars, they are slow rotators, so we can go to the non-rotating limit and ignore rotation and the electric fields that rotation induces. But we have to assume that some currents flow in the magnetosphere, and the origin of these currents is the interior of the star. So internal processes, crustal motions, and other things, magnetothermal evolution in the interior of the star, displaces the magnetic field, the magnetic field lines, and this induces helicity and energy to the magnetosphere and produces currents, which are important in understanding the transient, the flaring activity of magnetars. So we will assume that we have currents in the magnetosphere, but they originate from the interior, and we will only model them using some assumptions of how they look at the surface, not how they actually are produced in the interior. So all these assumptions give rise to some twisted configurations. So you have the magnetosphere of the star, and the field is not purely dipolar, but instead it has twisted magnetospheric configurations and magnetic loops and other characteristics like that. So the equations that all these assumptions give rise are this one, these four essentially, because it's a vector equation. This term here comes from the general-relativistic corrections. If we were dealing with a Newtonian case, it would be 1. And this term here, alpha, is what encapsulates all the information about the currents coming from the interior. So this essentially says that, in a way, the currents that flow in the magnetosphere are parallel to the magnetic field. They only flow parallel to the magnetic field. This force-free, this is the force-free assumption. This force-free function here, alpha, is a function of space, has to obey this constraint, which it's very easy to show, and it merely states that this alpha is constant along field lines, but different between different lines. Okay. So, a pause here. This is the problem that we're trying to solve. I'm going to speak about the method that we use to solve it. The method is physics-informed neural networks. So I will first talk about a little bit about neural networks without the physics part, and then explain how we use neural networks to solve differential equations. So I'm not sure what level everyone is familiar with this, but to explain it in a fundamental level at least, neural networks are functions. They get some input, they do some calculations, and they produce some output. The way that they do these calculations is taking the input, applying a linear combination, evaluate it through a nonlinear function, and give a number to the next layer, different linear combination for each node in this layer, and then do the same for the next layer, and the same for the next, and the same for the next. The principle behind all this is that if you know the optimal weights, this matrix W here, and you have enough of them, enough depth in your network, this is a universal function approximator. You can, in principle, approximate any function that connects your inputs and your outputs that you may initially don't know. You can approximate it by this representation. Okay. But of course, you don't know a priori the optimal weights to get the function approximation. So you have to find them, and this is called training the neural network. So you get all the set of weights and biases for all the nodes and the layers in your network. We will call them theta to have a compact representation. You construct a loss function. This is a measure of how well your function, your neural network, predicts known values that you already know how inputs map to outputs. So you have a set of data that you know, you want to train to find the optimal parameters that construct a neural network which approximates the function that connects your known inputs with your known outputs. So you want to minimize this loss function here. If the discrepancy between prediction and actual value is 0, then your function has learned how to predict correctly the data. The way that these are adjusted, it's simply solving an optimization problem. So you iteratively correct the initial random parameters that you have by doing small corrections, small steps. These corrections in general depend on the gradient of the loss function in the highly multidimensional space of the parameters, and also from the direction of the correction. So in this multidimensional space, you want to do a small correction of this magnitude, but towards the correct direction. I'm sorry. If anyone is familiar with neural networks, if you imagine that this matrix here is the identity matrix, so ignore it, and this is a fixed value, constant value, this is nothing more than a gradient descent or Adam. If this is something more sophisticated, like a Hessian matrix or an approximation of the Hessian matrix of the loss function, and this is again something more sophisticated, some algorithm to find the optimal step, these are more sophisticated optimizers for your neural network. And the key behind the explosion of machine learning and neural network in general in our current times is the way that you calculate this gradient here, which is again, it's not feasible to do it numerically, but there are some algorithms that track all the operations applied to the loss function, and then they know exactly how to get the derivative of this function with respect to the parameters, and this is called automatic differentiation. Again, is some usual tools that you use in neural network and machine learning research in general. Okay, so this is completely general from ChatGPT to whatever, Alexa or whatever. Especially regarding physics, hence the name physics-informed neural networks, we want to use a neural network to represent the function which is a solution to some partial differential equation that we were dealing with in our physical problem. So you can write a general partial differential equation. Here delta is a differential operator, it could be whatever, a Laplacian or a gradient or whatever, and S is a source term, so this is a generic differential equation. You want to represent the solution of this equation by a neural network, so it will depend on your the space and time and all the variables that you have, and also some parameters that construct the neural network. The difference between usual neural network training and physics-informed neural network training is that instead of having known values that you want to train your network on, find the optimal parameters so that some known data or observations are satisfied, what you want to do is train the network so that your equation is satisfied. So what you want is put your approximation of the solution for some point in your domain, and then demand that your equation, when evaluated at this point, is satisfied. So for this, you don't need any known observations or known data or having solved with some other method your problem and then try to reproduce it. You can just demand that your prediction, whatever it is, satisfies your differential equation. And if you manage to do this for a very big number of points in your domain, could be random points, you don't need to actually have them on a grid, then you can hope that the network has learned the actual solution of your problem and not just connecting points, inputs and outputs. This is the idea. So in principle, the idea is to just construct the loss function using your differential equation. This is an example of how the process evolves when you do this. So as I said, training is an iterative process. You just iteratively correct the parameters that form your neural network, and as you do it, the loss function reduces, which means that the residual of your differential equation when you use the neural network instead of the actual solution goes closer and closer to zero, which is what you want. And this is an example of the convergence of this type of solver. These small bumps here are occur when you change the points on which you train, because initially you don't want to only solve your equation in one specific set of points. You want to solve it in as many points as possible, and then hope that you are able to generalize to new unseen points. Okay. So this is the method that we use to solve the problem. We have the force-free equations. We use the pin solver to solve them. You want to produce various axisymmetric and three-dimensional models of twisted magnetar magnetospheres. In this particular problem, since it's an elliptic problem, we don't have time dependence. We only have the stationary solution, steady-state solution of the magnetospheric configuration. Everything depends on the boundary conditions that we impose on the stellar surface, and mainly the radial component of the magnetic field and the value of the force-free function at the surface, value of alpha at the surface. What we're going to do, we are going to evaluate the excess energy of the twisted configurations compared to the untwisted ones, the potential ones, and classify and qualify, let's say, evaluate our models based on this measurement. So first, we did some axisymmetric models. The axisymmetric models of magnetar magnetospheres have been studied extensively in the literature, but we wanted to validate our method and also explore some things about these models. So the idea is that you impose at the surface of the star a dipole magnetic field. This is a fancy way, a function that we use to define the radial component of the magnetic field. These terms here come from the relativistic corrections. In a Newtonian, let's say, setting, you would not have them. And in the axisymmetric case, the currents, the alpha at the surface, also depend on this flux function. And also some parameters, S and mu. Mu is constant here, we don't care. But what we are playing with is this parameter here, S, and also the compactness of the star, the ratio M over R. So one thing that is, here are all the families of the solutions that we encountered. One important thing that you can see here is that beyond this value of, let's say, maximum value of alpha at the surface 4, no solutions can be found. So no force-free solutions can be found. This means that force-free condition is violated if you increase too much the alpha parameter. And the second important thing here is that for the same value of, essentially for the same boundary conditions, you can find multiple solutions. So there is a degeneracy, and this is a problem because what you want usually is uniqueness. So you can see that each one of these lines, which correspond to different compactness, have multiple solutions for the same value of alpha max or S. And one of the two solutions has higher energy than the other. However, it has been demonstrated numerically, and also we have some criterion later that I can show, that the high energy solutions in this case are unstable. So they will actually not be realizable in a natural scenario. You can find them here because we are dealing with a stationary problem and we are solving for just a steady state solution. So this is a solution of the equation, but it's unstable dynamically. So you probably reconfigure your magnetosphere way before achieving this state. If you discard all these solutions, the stable solutions, and you consider only the stable ones, the maximum excess energy that you can find is roughly 30%. What we mean by excess here is that is the difference between the energy of the twisted case compared to the untwisted one, compared to the case with S equals 0 or alpha equals 0, the potential case, divided by the energy of the potential case. So it's the relative difference between twisted and untwisted solutions. So this more or less is was already known in different works in the literature. And these are some examples of such magnetospheres. So you can see here two solutions with the same surface boundary conditions, but different configuration, magnetospheric configuration. You can imagine that wherever you see colored here, you have a twisted magnetosphere. The field lines are not in the same meridional, they are displaced. And here you can see a 3D picture of this case, of this slice, where you have the magnetic field lines are twisted here, but you have some of them that are disconnected from the surface and form these disconnected regions. This will obviously never happen in a physical scenario. If this was an evolutionary process, you would eject the energy and go back to the stable configuration way before forming something like this. Okay. We move on to 3D models, which with the GR corrections was the first time that someone solved this problem. So in this case, we impose boundary conditions, the same dipole field at the surface, but for the current, we just choose a spot at the surface, a small region, where you have currents flowing from the interior, and this will give rise to a flux tube, let's say, of twisted magnetospheric lines that close to some other hotspot in the other hemisphere. I will show a picture of such solutions in the next slide. So we have here a pair of hotspots. Again, here we can see that I have drawn this line here, even though we have some models beyond this line, but I will explain later why these models, again, should be discarded. That the actually accepted stable and force-free solutions, in this case, can reach up to a maximum value of alpha at the surface, let's say, of roughly 2.5. This is measured in 1 over stellar radius. And in this case, the maximum excess energy that you can get is only 3% compared to the untwisted dipole case. And again, if you consider relative difference, this has a weak dependence on the compactness. So mostly if you have a compact star or a Newtonian star, more or less, the dependence on the energy is the same. But if you actually calculated absolute differences, these lines would not coincide because the energy of the relativistic state is higher than the energy of the non-relativistic one. Here are some examples. This is a compact star with a small twist. This is a compact star with a high twist. And this is the same twist as this model, but in the Newtonian case. So you can see that there are some differences. The twist is more confined. The inflation of the magnetosphere due to the toroidal pressure is less in the relativistic case than in the Newtonian case. So there is some effect even visually from the relativistic corrections. Okay, so these are the families of models that we solved for, and now we want to have some discussions about them, get some useful information. So the first one is we want to evaluate the stability and the existence, as I discussed even before. because the neural network has an advantage in the sense that when you solve the problem, the solution is local. You can predict the solution in one or in only one point, and then in all the points in your domain, but not as a grid. And this means that you may have a converged solution somewhere in your domain, and the solution is not correct or not converged somewhere else in your domain. And the code will not crash. The neural network will give you one response for this entire model. So it's up to you to evaluate if what you get is correct or not. So one way to determine if your solution satisfies the force-free criterion or not is to use this alternative definition of the energy in the case of force-free fields. This can be found in the literature. Compare this alternative definition with the usual definition of the magnetic energy. And if these two do not coincide, this expression is valid only in the case of force-free. So if these two definitions do not coincide, this means that probably your solution somewhere violates the force-free condition, and this is indeed what happened in our case. This is why we chose this line here to exclude and discard the models that do not satisfy this criterion, this equality. Another way to check if your solutions are stable or not is to use the so-called safety factor. Safety factor is a criterion per field line, let's say, used usually in twisted fields to determine if your field is prone or not to instabilities. It is defined as 4 pi over alpha. Alpha is constant along one particular field line, so you can label the field lines based on the value of alpha that they have at the surface, and it will be the same everywhere, and the length of the field line. So this product here essentially gives you a measure of how twisted your field line is, and if it's too twisted and too long, then it will be unstable. If this safety factor is less than 1 or approaches 1, this means that you are prone to instabilities. So we did this for some of the models that we have. All the models that we qualify as stable, like the blue ones here, have indeed safety factor bigger than 1 for all the field lines. Here we only plot the most twisted ones, but essentially this happens for all of them. But models that we qualified as unstable or violating the force-free, actually unstable, have some small bundle of the field lines violating this safety factor criterion, approaching 1, and which means that it's expected that stable force-free solutions of magnetar magnetospheres will occur roughly for the values of alpha that we have found in this work. So these are two complementary ways to evaluate the solutions that you get. Okay, I'm going to try to explain this because it's always difficult to get the message. So if you consider relativistic magnetosphere with a fixed magnetic dipole moment to determine the surface field, the relativistic corrections will give you a higher value than the Newtonian case. It was this bracket with the logarithm that depended on the compactness, if you remember in the definition of the boundary field. So this gives you a higher energy if you just naively evaluate the energy from the energy of the model that you have in your code. But in reality, the luminosity, let's say, of your star, if you include some relativistic corrections, the spin-down luminosity is overestimated if you don't include the relativistic corrections. This means that people, when they infer the magnetic field of magnetars, they don't have a magnetogram to measure exactly the field. They just infer it from the timing properties, which are measurable. If you do not include the relativistic, some relativistic corrections, not the ones that we have included in our equations, but when you infer the value of the field, you end up with a value which is 5 times higher than 5 times high. Okay, if you, the actual correct relativistic expression for the field that you infer is lower than the one people usually report for neutron stars. And ask me again if this wasn't very clear. This means that if you put everything together, even if the space-time curvature amplifies the surface field, if you put real numbers in this, you would need to put a smaller reference value for the surface field. And this means that in the end, the energy that you calculate from relativistic magnetospheres is lower than the energy that you calculate from Newtonian magnetospheres.
So you mean that, for instance, the requirement of having magnetars with magnetic fields as large
maybe not. Maybe yes. This is a general problem in the literature. People do not take this into account, and they infer fields very higher than probably they are. Okay, even so, if we take all the observed, some of the observed X-ray bursts from magnetars and put them and compare them with the excess energy that we have from our models, which at maximum was 3% for 3D models with just one twisted loop in their magnetosphere. This excess energy is enough to, if it reaches a point of instability and then the energy is released as X-ray emission, the stored energy in this case is enough to explain almost all of the observed outbursts. With the exception of one, this was a giant flare, if I'm not mistaken, which again, it was an extreme event, and it probably involves maybe some more global reconfiguration of the magnetosphere, maybe a magnetosphere with more than one twisted loops, or a big, let's say, global twist. If instead of the 3D models, which are more realistic, you consider the axisymmetric ones, which by definition are global, all the magnetosphere is twisted, then again, the 30% that we had as a maximum, and even taking into account all the corrections in the energy that I discussed in the previous slide, is enough to explain all of the observed X-ray activity, bursting activity of magnetars. Okay, this is my last slide. I don't know if I'm good or not in time. A brief discussion about gravitational wave emission from magnetosphere. So one of the things that we want to do with these models is to see if the contribution from the magnetic energy density of the magnetosphere to the mass quadruple moment of the star could produce observable gravitational waves. So you can calculate this integral here, putting the magnetic field of the solutions that we have. What we found is that this does not depend on the twist too much. So here there is some structure to these curves, but if you see the axis, the difference is very small. So the idea is that no matter how twisted the magnetosphere is, the gravitational wave emission would be more or less the same, so universal from all magnetars, and it would only depend essentially on the magnitude of the magnetic field at the surface. So if this could be observed, this is a another mechanism, another way to calculate the surface field and compared with what is calculated by timing properties. Okay, however, the magnetospheric contribution is way smaller than any contribution coming from internal deformations of the star. So in terms of amplitude, this is way smaller than other contributions, so it would be difficult to distinguish it. But the polarization properties of the magnetospheric contribution are different than the polarization properties of the internal contribution. So even if the amplitude is way smaller, you could in principle distinguish between the two. And this is always there because a magnetosphere exists. All magnetars have a magnetosphere, and independent of the twist, you would have some contribution. Now with current telescopes, gravitational wave telescopes, this is not possible to be detected, but with future ones, and I think DESIGO would be probably the most appropriate one because it peaks at the rotational period of the magnetars. If you have some multipolar field in the close to the star and a high enough field, in principle you could detect this kind of contribution, and this could be complementary, say, information to the ones that we have already from timing properties and electromagnetic contributions. So this is it for me. I'll summarize that the general-relativistic effects are important. In general, you do have differences in the magnetospheric configuration and in the emission that this produces if you include the relativistic correction, so it's important to do it. Pins is a pretty accurate and efficient method to solve this kind of problems, and I have compared this with other methods, and pins are, from what I have used, the best way to solve this problem. And in terms of the results, you get enough energy to explain the observations from these models that we have, and there is a possibility of some magnetospheric gravitational wave emission to be observed with to be detected with next generation instruments. So this is it for me. Thank you very much. Happy to have any questions.
Thank you, Petros. We have time for some questions.
Thank you for your lecture. I have a couple of questions. The first one, how do you build your training set? And the second is, how do you control overfitting?
Okay. So pins have some differences compared to more conventional machine learning applications, because you don't actually need a fixed training set, because you are not comparing prediction with data. You just need some random points in your domain, which you don't need to know the solution at these points. You take these points, you evaluate the function, and then you apply the derivatives that you need to apply to construct your equation. And what you want to make sure is that you satisfy the equation for any point. So you don't need to have a specific number of points that you know the solution there and compare the prediction. You just want, for any point, your equation to be satisfied.
So you start by the solution and
yes. So essentially, what we do is we give random points, and then we change these random points, and then we change them again, and then we change them again. So you have many random points in your domain, and you want all of these points to satisfy the equation. But afterwards, your solution is not calculated only on these points. It's calculated. You can use any new random point and evaluate the solution there. So if you have converged, this would give you the correct solution even in the points that you haven't trained for. in terms of overfitting, you don't have in the conventional sense that you have data points and then you may overfit these and lose the rest of them. But you can have a problem if your selection of points is not random enough, or it doesn't cover appropriately the entire domain, or even worse, if you have more structure in your solution in one part of your domain and less in some other part. So you will probably need more points in the part where the solution is more complicated than in the points where the solution is not so complicated and easier to fit. So you have to play with how you select your training points in this sense. But you are not afraid of overfitting to specific points that you choose, because they are random and that you change them continuously.
Okay, thank you.
Petros, okay, very nice presentation, and I have two questions, a technical one and a physical one. The technical one is related to PIN method, because you consider, okay, you have a problem that has some symmetry, and actually it's stead in time. So you essentially solved the problem in space. Yes. What about using PIN when you have the set of differential equations in a system that evolves with time? It means that you would have to train in every time step. So can you comment on this, how efficient it would be,
yes,
the method?
Yes, good question. If you know that the time interval that you want your solution, you can treat time as one extra input.
Yeah.
And use the same idea that you don't get only points random in space, but only also random in time.
So that you can predict the evolution,
yes,
right?
But this is not predicting. You have to define your interval. So you want to train from 0 to 100 time steps. You have to give random time points between 0 and 100. If you then want to predict outside of this domain, it will probably extrapolate bad. This is good because you can use exactly the same setup as here with one extra input. Of course, you have to get some bigger network in order to be able to accommodate the extra complexity, but the principle is the same. There are other approaches, other methods that instead of training to find the solution in specific time and space points, they train the solution to predict the next time point, which is the next time step. So essentially, this means that they don't solve for the actual solution, but they train to approximate the operator. What happens if I apply an operator to go from one time step that I know the solution to the next step that I don't know? There are approaches to do that. I haven't done it myself, but it's in the same area. So this is something that I always wanted to explore, let's say, but never had the opportunity.
It's one of the of the topics of your project in my group, right?
But yes, it's a big field also in the literature. It's a big topic.
Right. And the other question, if I may, it is about the force-free violation, right? Because of course we know that the force-free condition, it violates the energy conservation equation if you try to integrate the system entirely force-free up to the infinite, right? Because force-free, it's within a finite confined region, right?
I don't agree with that. If this is true only if alpha is constant.
No, not actually. This is in general. For force-free fields, you can use, for instance, the energy conservation equation, the virial in the plasma with all the terms, and you can demonstrate that the force-free will violate if you try to keep the system force-free up to the infinite.
Okay, if you include
it is valid
fluid
only
terms.
Exactly. It is valid in
Okay.
finite
Yeah.
regions, right? So then you found out that in fact this is what you verify, but it was not clear to me how you what it was the radius. I mean, physically speaking,
Yeah.
if the magnetosphere of the neutron star has a force-free solution. It is a force-free field. Nevertheless, the magnetosphere, you know, if you keep measuring magnetic field up to the infinite, this configuration is not going to be force-free forever. And this is okay, because this is actually what might occur. But in your case, you got this violation
Only for some models.
exactly. So and then I was trying to figure out how you got this, and the physical radius above which it is violated.
I'm not sure if so we let's say if we calculate this integral here,
that is the total magnetic energy.
the total magnetic energy up to infinity,
it diverges.
This does not diverge in our case. This does not diverge.
Yeah, it will not diverge if you finish the force-free condition.
But we don't. We actually, so we have some, this is a little bit technical, but we don't use, we use spherical coordinates, but for the radial coordinate, we use the inverse of it, which is some type of compactification. So if you use the inverse of it, instead of going from 1 to infinity, let's say 1 being the stellar surface, your domain is from 0 to 1, and 0 being the infinity in this case, because you use the inverted coordinate. So in this sense, we do integrate up to infinity. And this does not diverge. But this is because we don't include rotation, so the magnetosphere never opens. And we don't include any fluid terms. So this integral here in our case converges up to infinity. Does not diverge. But I'm open to discuss this with maybe there is something missing in the.
If you keep
but in our case, this and we go up to infinity in this compactified domain does not diverge. But this expression here, for some models, is not equal to this. I don't know if the discrepancy comes from the infinity or from the close to the surface, probably closer. But this is what we are doing here, comparing this expression here with this, but not in terms of which one converges or not. Just that this expression here is valid only, which comes from the virial theorem, is this expression here is valid only if you have a purely force-free field, and if you twist it too much, then it's not force-free, and this expression is violated.
Yeah, we can discuss this conservation later.
Hi, thank you for your nice talk. Can you comment on how this static force-free conditions is used to explain the actual eruptive energy in the which is available in the dynamical resistive magnetosphere?
So can you repeat?
So you consider a static force-free condition to explain the dynamical flare. So can you comment how you can how it is validated? This force-free condition in the.
So we solve this equation here for different values of alpha, let's say at the surface, which determines alpha everywhere. For different values of this alpha, the magnetosphere would be more or less twisted. It would be.
A twist is physical or numerical?
No, it's physical. So if you take a picture of the magnet of a magnetar go close, you would see the magnetic field lines like this. So not closing in the same meridional, let's say, as it would in a potential case, but having some current, or everything that has color here has some current flowing along the field line, so has particles flowing along the field line. And it has currents, electrical currents, and it closes somewhere else, so it has to get this weird configuration to be able to sustain these currents. as you have more and more current flowing from the surface to the magnetosphere, this would be twisted more and more. At some point, this would have higher energy than the potential case, the ones without any twist, just a pure dipole. So the idea is that as you twist it, you store more energy coming from the interior, and at some point you will reach a point of instability or non-existence or whatever. In the magnetosphere, you would have to, if you had a dynamical simulation of this, you would see that the magnetosphere reconnect or do something, expands some type of bulb or something, some magnetic loops that will break, go back to a more potential state, and all this energy is what goes then to the particles and emitted as a flare, as an X-ray.
But you have ignored the magnetic, the plasma effect.
Yes, we just because the plasma effects does not determine. So this is not a dynamical simulation. The plasma does not affect this configuration because the magnetic force is way stronger than anything that the plasma can do. So only the magnetic field determines this configuration and the limit that you can reach. But after you reach the limit, obviously, of course, there are particles there. They will get this energy and they will then emit. But here we just essentially explore the limits. How much can you twist the magnetosphere? And the idea is that if you twist it too much, something would happen that in a dynamical simulation you could see. But it would not be easy to reach all these, maybe even earlier than this. So here we achieve some extreme twists, but maybe you never get there. But it's easier to solve the steady state problem than a full simulation of.
Thank you.
Thanks, Petros. I was wondering, when you were showing the excess energy as a function of alpha, you have the degeneracy.
Here.
What is causing this degeneracy in your simulations?
Well, the problem is the equations do not have a unique solution for the same boundary conditions. And this, again, this is not easy to. This you would never be able to see it in a dynamical simulation because you would never follow all the. Essentially, what happens is that both these, let's say whatever, here, this point and this point, are solutions of your equation. And if you start from this one and tweak only slightly the boundary conditions and then solve, you would get this. Then again this and this and this. You could follow all this trajectory by following the sequence of solutions with very small differences. What is causing this is, well, this is an artifact essentially of axisymmetry, because you could construct something like this. Well, actually here, if you want to see it in a 3D, with all this black thing is a disconnected region with field lines following it, which is disconnected from the rest of the from the surface, which originally. So this is just an artifact of building steady-state solutions. Physically, you could imagine that you twist, and then you reconnect the lines, and then you this island. I don't want to say this word, but this is an artifact of. This is a force-free solution, valid force-free solution for the same, which has the same surface boundary condition as this one, but has this disconnected region inside. This is why it is degenerate. In nature, you would never arrive here, or in a simulation. You would never arrive here because you would reconfigure the magnetosphere way before arriving at this point. But since it is a solution, we can find it by solving the steady state problem. This is
okay, thanks.
Can I? Hi, Petros. Thank you so much. It was a very nice presentation. I have way too many questions, but we can probably discuss later. But just to do some questions here. I was a bit more of a technical one. When you show the convergence of the solution, and you're mentioning that this is an iterative process, what are the iterations exactly? Like what is?
The iterations are these ones, the iterations on the parameters of the neural network.
Okay, so,
So you have a
when
neural
you
network.
change the parameters.
Yes, you change the parameters by doing this step here, and then you predict again, you evaluate the loss function, it's not good, you correct again and again and again, and every time it's a little bit better until it reaches some kind of.
I was just wondering what happens when you compare two neural networks that were trained on different number of points in your variable space. Like how does this convergence that you're showing depends on this?
Yes, you can make a map and see where it converges better or worse, but essentially what your criterion is the sum of all. So here is a sum. Obviously, in different regions, and this is in different regions, the convergence may not be the same. So the equation may not be equally well solved everywhere in your space, but your measurement here is the sum of all of them. There are some techniques to give more weight to some region or the other, or maybe use the maximum so that you are sure that at most this is the error. But yeah, this is let's say the surface of what you do. But there are more tricks underlying.
And in a more physical question, have you considered quadruples in your boundary conditions?
Yes. No, I don't have them here, but
what happens?
Yes, you can do it easily by modifying this function, obviously, to put a quadruple, and you can do the same analysis. We didn't want to do an exhaustive analysis of all the parameter space. The quadruples are even more important in maybe in the gravitational wave emission, because they affect the detectability. Let's say if you have or don't have quadruples at the surface. But yes, it's easy to do with multiples. Let's say at the surface. Yes, if you it's more complicated. The expressions for the multiples are more complicated in the Schwarzschild metric, but they are written somewhere, so you can use them. It's not.
I will ask you other questions later. Thank you.
Let us thank Petros again. And see you all next week.